we are here to present the Flux framework tutorial. As I said, I'm Dan Milroy. I am a computer scientist at the Center for Applied Scientific Computing at, obviously, Lawrence Livermore National Laboratory. And I'm joined here by my colleague, Vanessa Sockett. We're going to be kind of tag teaming, going back and forth, presenting different slides and material, and then we'll be both available after the slides to help you kind of walk through examples that we prepared. And we may also have, I'm not sure whether other folks from the development and research team can join us, but if so, we'll also have those folks in the tutorial session as well. So as you can see, we've got a decent number of people that help out on this project, that do tremendous development and research work, and really kind of stitch together this framework. All right, I figure we can get started. So I mentioned the Flux framework. And what is the Flux framework? We also consider the Flux framework to be Flux. This is another name for it. But it is a software framework that combines basically a system workload manager, or is a system workload manager, that combines two really important features. One is hierarchical job management, resource management, and also graph-based scheduling. And if you are confused by that division between or job management or resource management and graph-based scheduling, you're not alone. I was when I first started working on this project, and hopefully by the end of this presentation, you'll understand a little bit more about how we've divided up these different components and exactly what benefits that division brings. So as you saw, many of the contributors and researchers behind the Flux project in the intro slide, we have well over 15 contributors at this point. I think, in fact, actually over 20, including some of the principal engineers who created Slurm. And we have a lot of expertise, as you'll see, in container technologies, scheduling algorithms, and also cloud computing and integrations with cloud computing. So for those of you who aren't familiar with the term workload manager, I bet most of you are, but for those of you who aren't, we define workload manager to be something that receives units of work, and you can consider that to be scientific simulations, and that could be an ensemble of individual scientific simulations. And this workload manager makes sure that they are planned, mapped, assigned, executed, managed on typically many computers, or in particular a supercomputer. So an example of the type of workflow that Flux was designed to support, we have here kind of a complex, almost converged scientific workflow called the autonomous multi-scale workflow. And this combines kind of traditional HPC features with services and messaging components into a coherent workflow. So it's got a multi-physics model that uses MPI. So this is kind of the traditional HPC component. And it also has a surrogate model. And the surrogate model or the multi-physics model execute depending on a decision that the UQ module makes. In other words, has it seen inputs that are close to these inputs in the past? If so, it will execute the fast surrogate model, which is a machine learning model, or it will execute the expensive multi-physics model. And if it does that, then it's going to save those input-output pairs in order to retrain the model itself. So you go through all these sorts of dynamic processes within this workflow, whereby you save input-output pairs and you use those to periodically retrain a model and then distribute that surrogate model back to the workers who are then going to perform more inference. So this combines also services like RabbitMQ. You can see we have Kosh databases. We have a daemon that's running in Kubernetes. We have all these components that need to be orchestrated together. And it turns out that that's very, very difficult to do with traditional workload managers and schedulers. So we also have new emerging workflows that have complex and heterogeneous components, much like AMS. But in this case, you see here MUMI, or the multi-scale machine learned modeling infrastructure. This has actually been re-architected many, many times before. And initially, or many times when you've seen versions of this presentation, one of us has talked about the previous architecture of MUMI and what that looked like and how that was already challenging workload managers at pre-exascale. Now this workflow has been redesigned many times, and it is it is now more tightly integrating cloud components. So you're seeing kind of movement towards converged computing. So I want to kind of walk through or highlight some of the different components of this workflow. So first, it has a machine learning or AI component, and that's the structure generator. Then we have a simulation component that's based on GROMACS at this point. There's an orchestrator, so that's a workflow manager, could be Maestro and Flux working together, or as you will see later, other methods in order to orchestrate this workflow. And then it has service components, much like you saw in the previous slide for AMS. It uses RabbitMQ. Now, how do these workload managers actually help? Well, they help in order to manage and schedule the heterogeneous resources. So think of like different architectures, CPU architectures, different accelerators, GPUs, devices, etc. And these need to be scheduled, managed, provisioned in a fair way. And that fair part is important as well. So I want to highlight that Flux is the system scheduler on El Capitan. And for those of you who haven't heard, El Cap debuted last year at #1 on the top 500 list. But we also, and when I say we, I mean the Flux Framework team, have quite a bit of presence in the rest of the list too. So we're also managing and scheduling Tuolumne, which is also at the laboratory. We have El Dorado at Sandia, and then 3 other machines that were kind of early access machines to the Coral 2 systems like El Capitan and Tuolumne. But Flux actually deploys across clouds and virtual machines as well. We built up a lot of infrastructure and techniques in order to easily deploy Flux on a lot of cloud native technologies. So for example, in AWS, we've done a lot of work to make sure that Flux works with the Elastic Fabric adapter. We've done a lot of testing and research and experimentation to get Flux to work well on the HPC family of instances, whether that be within EKS, and that's the Elastic Kubernetes service, which you probably used in one other variant or previous variants of this tutorial, or on EC2 raw VMs. Now, we've also done a lot of work on Microsoft Azure to enable InfiniBand Fabric for AKS, and that is the Azure Kubernetes service, via kind of comparable instances like the standard HB120 v3s, and others as well that support GPUs. And we also work on VM sets too. Finally, we've done quite a bit of work getting Flux to work with the tier 1 networking in Google, and this is on either GKE, and that's the Google Kubernetes engine, or Compute Engine itself, which provisions and manages virtual machines. So the point that I'm kind of trying to make on these previous 2 slides is that Flux is really agnostic as to where you run it. So it's designed to be the system level scheduler, exclusive scheduler for an HPC system. It's designed to run in user space under another resource manager. So think of Slurm, LSF, PBS, etc. As on it by itself, on your laptop as a single Docker container, as an orchestrated set in Docker Compose, a full Flux cluster running inside Kubernetes. This is a mini cluster, which you'll see a little bit later. And we have kind of native virtual machine setups that work across clouds. So we've got all sorts of different wonderful deployment strategies that we've developed for Flux. Now, to step back a little bit and to give you a timeline for the Flux project, it really came about in 2012. That's when the project was established. That's when the project was funded and the proposal was funded, and then the project was staffed. Went through its design and preliminary review in 2013. The first instance was launched in 2014, and Flux was originally designed to be launched underneath external resource managers and schedulers, and I'll talk about some of the advantages of that in just a bit. 2016 was when it was released publicly, or Flux Core was released publicly on GitHub. Then the first public executions of scientific workflows were done in the pilot 2 Cancer Moonshot Ensemble in 2018. Then 2019, I think you probably noticed on the previous slides on Mumi, Mumi won the Best Paper Award at SC19. So we were running that workflow on Sierra at that point. Then the system instance, and this is the instance that actually manages and schedules the entire machine, was released in 2020. We had updated integrations for the Mumi workflow and yet another SC paper in 2021. And then, as I mentioned before, in 2024, El Capitan debuted as #1 on the top 500, and again, Flux is managing and scheduling that system along with its sister system and other related or other systems like the one at Sandia Eldorado. So I've talked a lot about Flux being designed to handle more complex workflows. So let's get into a little bit about what makes Flux special and why it is that we needed yet another resource manager and scheduler. Well, I provided some hints when I talked about how Mumi has been re-architected a bunch of times. When it was initially designed, it was extremely difficult to set up and deploy, given all the different components, because it had requirements for flexibility, for portability, and yet specificity in terms of exactly where different components of it would run in order to make sure that the workflow performed well. So all those capabilities together, kind of components plus portability plus flexibility plus performance, meant that those types of workflows would challenge existing resource managers and schedulers. So we came up with some of the needs that were exemplified by these workflows, and then going forward in the future, kind of converge workflows that are integrating more cloud technologies. So emerging workflows and systems really need a flexible resource model. So think of flow-based resources like network, power, storage to a degree, and then some other future resource that we haven't even thought of yet. They're typically not easily integrated into existing schedulers. If you want to define new resources, a lot of times you have to restart the scheduler, which can be kind of inflexible and difficult. However, we present a flexible resource model, and I'll talk about that in a little bit, or Vanessa will talk about that in a little bit, which can express effectively arbitrary resources, and as I said, kind of those that don't even exist yet. I mentioned before the characteristics and the capabilities of a hierarchical design. Well, it really facilitates portability, among other things that I'll talk about in just a moment. So the resource manager or Flux can be thought of as a job or instantiated as a job under itself or another resource manager. And that kind of speaks to the need for portability. So the resource manager itself can be a portability layer. Think of it as you need to program your workload or workflow to Flux. And once you've done that, you can transport it across other resource managers, including cloud resource managers, without having to restructure your workload or workflow. As I said, kind of re-emphasizing that we support deployments on Kubernetes, on, of course, native HPC, and on virtual machines as well, both in system space and in user space. Okay, one of the other features that is afforded by the hierarchical design is scheduler configurability. So you may ask yourself, well, do you want only one scheduling algorithm? Do all components of your workload actually only need one workload manager or one scheduling algorithm? And if you answered no, or you answered no to only wanting one queue algorithm, then we've got a solution for you, and that is again using the hierarchical and modular capabilities of Flux. At each level of the hierarchy, you can actually tune both the scheduling algorithm and the queuing mechanism. So you can use a first match policy at one level below, a full graph search at the third level, etc. Now, to kind of reinforce this, instances can actually be created hierarchically, and you can partition and manage the resources according to the workload needs. So this slide is kind of modeled after the initial capabilities needed by the Mumi workload or workflow. So for example, you have a training job on Flux 3, one of the followers in this case, that uses odd numbered cores such that they're closest to the GPU. And then there's going to be a different set of work that's going to be running on the even numbered cores. And you can do these sorts of things or make these sorts of management decisions with Flux relatively easily. One of the other things that we're working to support is scaling up and down. Let's call this dynamism and elasticity. So a traditional approach with static allocations can lead to underutilization of resources, depending on kind of flexible resources or changing resource needs over time. I mentioned a variant of this in the AMS workload or workflow. We are working really hard to support kind of end-to-end elasticity, both in the scheduler component and the core component. We support some forms of elasticity now, and we're working really hard to make sure that, as I said, we have support all the way through the infrastructure for it. If you're curious about specifically what we support, I have a few slides at the end where I'll talk about where we are in terms of elasticity. All right, so with that, I'm going to hand over to Vanessa so she can talk about the architecture and projects.
All right, so I'm going to be talking about Flux architecture and projects. So why is Flux a framework? Flux is a framework because it's actually several different projects that when you put them together, they manifest in the workload manager that we know as Flux. This is really great from a design perspective for developers because it means you can take these components, put them together in creative ways to come up with new applications. So for example, we've taken Flux Sched, because it's modular, we can move it into the Kubernetes space as a custom scheduler plugin. Now, we don't play favorites for our children, but we kind of do. So the main projects that are sort of the most important in the Flux universe are Flux Core and Flux Sched. So Flux Core is what you interact with on the command line when you Flux run, Flux submit, Flux alloc. That is the Python SDK that lives inside Flux Core. Now, Flux Core is also responsible for job management. So when you Flux submit your job, there's going to be steps to transform the job in different ways, to validate it. You may want to get a status. That is all living in Flux Core. It's sort of this central hub. This also means that's where messages and events are sort of primary located. So Flux Core is going to be sending and receiving messages to other components. One of those main components, of course, is Flux Sched. Flux Sched is also known as Fluxion. So if you hear the term Fluxion out there, that's what we're talking about. And it is the main scheduler for Flux Framework. So what does it provide you? Well, it's going to give you a resource definition. This is a serialization format for your resources. This can be in JSON or XML and a few other formats. It also comes with a really rich set of queuing algorithms. So for example, first come, first serve, add backfilling. Those are all sort of modular within the library, so you can look at them, you can understand them. You could also probably write your own if you're interested. And of course, the very important component of Flux Sched is the resource graph. Flux Sched models your cluster as a graph. So for example, vertices will be nodes, cores, sockets, and then of course the edges will be the relationships between them. So for example, node 1 contains socket 1 contains some number of cores. And a little known fact about Flux Sched is that it actually contains a query interface. We use this for testing, but we also use it for running simulations and experiments. So for example, this summer, we have a lot of very talented grad students that are doing a lot of really cool work using this interface. Here's an example of what a tiny cluster might look like as a graph. So at the top in blue, we have our tiny cluster. That's the root node. Under it in red, we have 2 racks. Each rack has 2 nodes. Those are in brown, so we have a total of 4 nodes. Under each node, we have a socket that is in green, and then under each socket, we have 4 cores. Now, you can imagine that when you submit a job and you say, hey, Flux, I want you to match what I want for resources to this graph, and then allocate me those resources. The way that we traverse the graph, the decisions that we make at each node in terms of traversal, in terms of counting things, this comes down to how the scheduler works with respect to policies and then pruning. We're not going to get into that in this talk, but if you're curious, we can talk more about it at the end. So Flux Core, you can imagine it as like the entity, the guy that you're like talking to when you want to submit work or do anything with Flux, like, hey, over there, hey, Flux, I want to run, here's my job. I want to run a job with these resources. I want to watch the job, and I want to respond to events and do something interesting in a language SDK of my choice. Actually, I changed my mind. It's wrong. I want to cancel it altogether. I want to check status or get job info. Or if you're sort of a more advanced user, you may even write custom plugins, not just to validate, but to do other interesting things with your work. So here are some examples of what those commands look like. And if you've never seen Flux before, don't worry. We're going to have a lot of these examples later in our tutorial. Here's an example of saying, OK, I want to run a job, my app, with 4 nodes and 384 cores. So Flux Run is blocking. That means that, for example, if you Flux Run lamps, you're going to see each line of lamps appear on the terminal until the job finishes, and then it will give it to you back. If you don't want it to be blocking, you use Flux Submit. So we can Flux Submit the exact same work, and instead of seeing lamps, we're just going to see the job identifier right there. And then you can take that job identifier and you can further interact with it to get information, status, that sort of thing. Now, the set of commands that are analogous to this in kind of the batch space are alloc and batch. So if I write a batch script that has some number of Flux directives and commands in it, that I can use Flux batch, again, the same number of resources, and that's going to create a new instance, then run that work in the instance. That is non-interactive. Of course, if you want to actually shell into your Flux instance, poke around, run things, have fun, that's what you would use Flux alloc for. That is the interactive allocation variant. Alrighty, so I am now going to hand it back to Dan, who's going to tell you about some updates to Flux since our presentation last year.
All right, I am going to assume everyone can see that. Looks like it's operating properly. Interrupt me if otherwise.
Looks good.
All right, so yeah, we did a lot of improvements since last year. So for those of you who saw this this tutorial last year, we talked about improving scalability, resiliency, etc., and a lot of that was in anticipation of the deployment on the full LCAP scale. And as you noticed, we deployed on LCAP, so we did solve quite a bit of problems. We tackled quite a bit of issues that cropped up as you move toward 10,000 nodes and above. So we actually included some new features too, like batch submission directives. We made improvements to multi-user job signal handling. In terms of scalability improvements, in particular regarding the resource graph traversal, we enabled the ability to perform traversals more rapidly, reduce memory footprint via optimizing some of our graph traversal pruning techniques. We also improved queue throughput by making the queue much more asynchronous. We enabled faster string comparisons via string internal class, and that also translated to reduced memory footprint. As folks were asking, I believe in chat before, we support some elasticity, not full end-to-end elasticity. We're working toward that. Currently, we support grow and shrink of the resource graph, which is not the same thing as growing and shrinking the resource management component. We do support shrink of job resources. In other words, this is typically via what we call housekeeping. So think of these as like epilogue scripts. We're working currently on presenting that as kind of a porcelain interface for users to be able to hand back resources for large jobs. We currently support increasing the size of a running instance via marking resources as up. So think of this as analogous to how the Slurm Power Management plugin works. We have a lot of in-progress work to enable, again, as I said, the end-to-end features for elasticity, like adding brokers dynamically to running instances, and that's going to enable detection of new resources and then full integration into the scheduling component too. We have a whip out or work in progress PR out to grow an allocation, which then of course you can extend that to growing an allocation hierarchically, which is going to be our next step. Okay, I mentioned that we improved resiliency. In particular, we enabled resilient batch jobs, which are tolerant to losing compute nodes. We refactored, or we enabled the capacity in the scheduler to reload with running jobs, to change kind of the scheduling configuration a little bit without losing those running jobs. We now have support in the environment variables for using mustache templates. We have custom scheduling policies in the resource module. We enabled that. In terms of the Python API and interfaces, we now have a queueless class, which enables you to, or allows you to perform changes to configuration, status, the queues, the queue counts, etc. We now have resource and job events via a journal consumer interface, and we have support for running jobs under system D with C group constraints. We have a host or a slew of new commands. There's Flux Archive, host list. You can take a look at the man pages for details on these. We have resource event log for greater introspection or inspection of the event log and the ability to update Flux via command. We have the ability to debug and observe or increased observability for what some of the overlay is doing and what the component modules are doing via Flux module trace and overlay trace. And we have the ability to start from recovery files. So you can take a look at the Flux start minus recovery option. We can also do a batch with a dump option. You can take a look at that, how you can actually output some recovery files. We have, looks like we got a little bit of duplication here. All right, so let's I'm going to hand the baton back to Vanessa so she can finish things up and talk a little bit about how we're enabling converged computing.
Alrighty, so I'm going to be talking about converged computing. This is an area that continues to be exciting to me. We have been working on converged computing for several years now, and it continues to be exciting and it continues to be very relevant. So what is converged computing? Converged computing is really combining the best of both worlds between cloud and HPC. So you can imagine that both spaces have features that we really like. In HPC, we have tightly coupled applications. We have very sophisticated scheduling for a very heterogeneous hardware, sophisticated queuing. Cloud, though, also has a lot of really nice features: automation, portability, orchestration. And you kind of want to be able to take your two favorite things, shove them together, and then get the space in the middle. That space in the middle is basically converged computing. And it's not just the technology space, it is also the people space culturally, because we need to be able to work together, to collaborate, to achieve a lot of these goals. So converged computing really is a best of both worlds. As you know, cloud is an environment, public and private, that supports all of these features: portability, reproducibility, usually via containerization, resiliency, efficiency, reduced complexity via automation, all by way of things we've already talked about: elasticity, declarative management, auto-scaling. But what does the world look like right now? Well, where is the money going? Well, a lot of the money is going to cloud. So cloud is projected to grow to $1.28 trillion of USD revenue by 2028. That is a 20% compound annual growth rate. HPC is also growing, but more slowly. So HPC is expected to reach 100 billion by the same year, a compound annual growth rate of 8%. As you also likely know, the current landscape is very shaky for science, and funding streams that we've relied upon for many decades are being cut. So when we look at this picture holistically, what does it mean for science? What does it mean for workflows? Well, it means that the resources that we maybe have been running on for a long time, maybe they won't be available. The way that we've always done things is changing. And what we have increasingly started to see is that portability is becoming a new dimension of performance. You can't just, build an application for one cluster and expect that to be there in 4 years. It's really the case that there's many different resources available, HPC and cloud, and our applications and ourselves, we need to be flexible to move between environments. And so this begs the question: if we need apps to be portable, which scenario here makes sense? So on the left, we have sort of the traditional HPC way. I'm going to build this application. I'm going to optimize it perfectly for one environment. And indeed, that box that this carpenter has built, it is beautiful, it is crafted, it's probably perfect. But on the right, we have another strategy to build very good for many environments. And so what we're starting to see is that in a world where you really need to move between these environments, this strategy is actually better. And so where does Flux come into the picture? Flux comes into the picture because it is a portability layer between all these environments. Flux is actually analogous to Kubernetes, but the basic idea is that if you program your workflow or your workload to Flux, you can move it from HPC to cloud. You can move it easily into Kubernetes or on bare metal VMs in cloud. It is a portability layer. And as I mentioned, if you look at the design of these two projects, this was something we realized years ago, they are analogous because they're both composed of interchangeable components. We can take a component from Flux and build something in Kubernetes. We can even move Kubernetes and have it interact with Flux, and we're going to be showing you that a little bit later. So let's talk about some of these projects that kind of bring together Kubernetes and Flux. The first is the Flux operator. This is how you would deploy an entire HPC cluster in Kubernetes. This was a project we started at the end of 2022, and it's been hugely successful in terms of empowering us to do really great work. The basic idea is we started and we took our Flux components and we said, okay, we have these Flux components. How can we map them into Kubernetes abstractions? And so we did that, and we were able to implement the entirety of Flux inside of Kubernetes. We call that a mini cluster. This application that's running in Kubernetes that knows how to create these mini clusters, that is called an operator. You can think of an operator as an application in Kubernetes that knows how to manage objects, manage the life cycle of those objects. So what does this mean in practice? It means you're going to write a YAML file. So if you're not familiar with Kubernetes, there's a lot of YAML files. So for our mini cluster definition, this is called a CRD, a custom resource definition. You might start with your application container. By the way, the application container does not need to contain any component of Flux. Flux is added on the fly by the operator. If you're running your mini cluster as a job, meaning that you're going to bring it up, it's going to run the application and complete, then you would give a command. The other alternative is that you're actually bringing up an interactive cluster that you can shell into and do all your things and then bring it down when you're done. And of course, you would want to size the number of nodes. So the basic idea is that you're defining the cluster that you want. You give that to the Flux operator. The Flux operator looks at the cluster that you want. It looks at the state of Kubernetes, and it keeps making incremental changes, and that's what's called reconciling, until the state of Kubernetes matches the state that it needs to be to support your cluster. What is that state? Well, if we look here on the right, what we have is some number of pods. So each pod has a Flux broker. There's one lead broker, and then there's several follower brokers. The mapping is 1-to-1. We do that because HWLock is used to discover resources, and if there was more than one per physical node, we would actually be discovering more resources than we have. You get oversubscription. You can do that if you really want to, but we don't advocate for that design. The purple is what we call the T-bone, the tree-based overlay network that supports communications between the nodes. A really cool piece of work, this is new from this year. So to kind of step back to last year, August 2024, we did a huge performance study across clouds, Kubernetes. And what we realized very quickly is that even with Kubernetes that has declarative management and a lot of automation, we were doing a lot of manual work. You know, we would apply the YAML file, create the cluster, we have to shell in, interact with Flux, you know, save the logs, push them to a registry. It was a lot. And we said, you know, we don't want to do that again. That was too hard. And so what we created are what are called Helm charts. So Helm is actually considered a package manager for Kubernetes. It is not a package manager as we would think about one. It is technically a templating engine. But what this will afford you to do is to have basically a command. So right here on the left, what we're looking at is AMG 2023. With one Helm install, we can define our application parameters. So you see the problem size, the processor topology. We can define our mini cluster design, so the size, the number of nodes, the tasks, how we want the output logs to be generated, and the experiment design. So for example, run across all nodes, do this number of iterations. Maybe you just have a single node benchmark, or maybe you have a point-to-point benchmark such as OSU latency. And you literally can copy paste that once and then step back and watch everything. It will bring up the cluster, it will orchestrate the experiments, you'll get the logs in your Kubernetes output, and then everything will come down. And you can watch music videos and enjoy it while it's going on. So we have about 37 applications, and we have a paper that will be coming, that will be submitted soon that talks about this setup. Another really cool part of this setup is that there is a sidecar. So a sidecar is basically a container that runs alongside your application that provides programs with eBPF. So the eBPF is the Extended Berkeley Packet Filter. So while your application is running, you can look at basically anything that's going on in the kernel. It's a very low overhead way of doing this, and we talk about some of the overhead in this paper. Now, many people have different views of eBPF. I think eBPF is sort of this untapped, really cool technology that the HPC community, that will really help the HPC community in cloud. Why is that? Cloud does not typically expose performance counters unless you use very specialized instance types. Okay, so let's talk about a really exciting setup. So what I just talked about was like taking an HPC scheduler and moving it into cloud. But guess what? Converged computing is bi-directional. So user space Kubernetes and Flux is based on the idea of like, well, let's take Kubernetes and bring it back to our bare metal. Let's best utilize the resources that we have. Let's get all those great features that we want, the automation, the modularity via Kubernetes on the clusters that already exist. I don't want to build a new cluster. And so this is a project that we like to call the bare metal bros. So we have been working on this for several years. We started on premises with a private virtual machine cluster we called the Star Trek cluster. We realized very quickly that networking was an issue. It's because there's a component called slurp for net NS that requires packets to move through an additional tap device. It adds about 2 times overhead to running your application. However, we can get around that using a bypass mechanism such as the Elastic Fabric Adapter, so EFA on AWS, or InfiniBand. So we've done experiments and setups, and we have papers for both AWS and Azure. We do have a setup for Google Cloud, although to the best of our knowledge, there's not an equivalent device that we can use like that, so there's no bypass. And this year, we have our first production setup on premises at the lab on the Corona cluster that is using InfiniBand. So this is immensely cool, and we have a surprise for you at the end of this tutorial. I'm not going to tell you yet. So here's what this might look like. So for example, you basically would run a batch job. In the batch job, user space Kubernetes would be started for you. So you have the command line client that you use to interact with Kubernetes. That's called kubectl. And you'd also have Flux. So on the bare metal, you might be running simulations, right? But in Kubernetes or user space Kubernetes, you might bring up a machine learning server or a message queue or a database. Anything that needs to be orchestrated in that space, you can then have your simulations interact with those services. And it's all brought up in the context of a batch job, and it all is brought down when you're all done. Alrighty, so let's start the engines. I'm going to show you how to basically just open up the notebook, and folks can follow along and do this as we go. We are not entirely done with the talk, but I want to make sure that you know how to do this. So if you go to tutorial.fluxframework.org, you will see what looks like a Jupyter Hub interface, and it sort of is. So basically, if folks want to go there now and log in, so I'm going to be Dinosaur, and the password is, and Dan, if you can post this in the chat for folks, that would be helpful, Fluxtastic-HPCIC in all caps, and then 2025. And so I'm just going to kick this off so it starts loading. I just need to refresh that's just the browser cache. Dinosaur. Okay, don't save that. So that will start loading. Okay, I'm going to go back to my slides. Alrighty, so the surprise for you that we have this year, so normally for our tutorials, we use the Jupyter spawner. That means that in the past, you have gone to that interface and you've logged in and you've gotten a pod in a Kubernetes cluster. This year, we're like, you know what would be really cool if we let people test out user space Kubernetes alongside Flux. And so we built a new EC2 spawner that will give you an environment that has user space Kubernetes and Flux. We've revamped all of our notebooks, and we also have a new notebook that has some of that content. I'm going to be showing that to you. You aren't getting a pod. You are getting an entire node. It is an HPC 7G 16X large that has 64 cores. It's a Graviton 3 AWS processor, one of my favorite AWS nodes. And of course, as this little cute hamster points out, dark mode is perhaps the greatest accomplishment of all of mankind because it's just great. Okay, so one difference in the tutorial content this year is we're kind of framing it as a choose your own adventure. The reason is because we realize there's a huge breadth of experience levels in our audience, and we don't want to kind of enforce that, you know, if you've been here every year, you're like, I'm tired of learning about how to Flux run. I was doing this 3 years ago. So you can choose the chapter here based on your interest and based on your experience level. So if you've never used Flux before and you want to learn the basics, chapter 1 will be for you. This is our introduction to Flux. If you, for example, develop workflow tools or you want to interact with Flux and Python, get a Python SDK, chapter 2 goes into detail about how to use Flux Python. Chapter 3 is for the folks that like learning interesting tricks. So that is what we call Flux plumbing. This is where you're going to learn about Flux Archive, how you can basically move data between nodes without having a shared file system. And one of my favorite commands, Flux exec, to kind of send commands between nodes. Chapter 4 is the new chapter. This is Flux with user space Kubernetes. And this is super cool. We'll have you start running lamps on the bare metal, or basically on the virtual machine instance. Then you're going to run it in user space Kubernetes with the Flux operator. Then we have the Kubeflow trainer, so some AI ML training. And then we finish up with a cool interactive kind of simulation that uses both at the same time. So let me give you a sense quickly of what this environment, what you're interacting with, so you understand when you shell into a notebook, like what's under the hood. So what you're looking at here is what you would expect on a production cluster. So this is under a batch job. In this environment, there's going to be one Kubernetes component, whether that's the control plane or a kubelet, backed to a physical node of the Flux broker. So for example, UHPC0 has a control plane, UHPC1 has a kubelet. And on the right, you are going to have rootless Podman or Docker, along with kind of these standard Kubernetes components. So when you go to that interface for the spawner, you start on the hub. So that's on the left. You see the login. You log in. When you get to your notebook, so this is the launcher page that you'll see. By the way, there is a dark mode. I think it's under tools or settings for those that are blinded by the light like I am. So I want to point out that when we start with the Flux start command, we give a test size equals 4. And I want to explain what that means. Now, if I had just done Flux start Jupyter Lab, Flux would see the actual resources of the node. It would say, okay, there's one node with 64 cores. However, a lot of our examples warrant having more than one node and say, so when we add test size equals 4, that's sort of emulating that you have 4 nodes. So basically, you'll do Flux resource list, and you will see that you have 4 nodes and 256 cores. I need to point this out because you do not actually have 4 nodes and 256 cores. So just keep this in mind. If you go wild and crazy with running lamps and you really up the problem size, that you can break things. Don't oversubscribe your job. I mean, you can if you want, but it's your node. And the reason this is a little bit different than the setup that we would have on a production cluster is because we do only bring up one control plane or one Kubernetes component for you to interact with in the space. And this is emulating sort of a traditional batch job, how you would use that on HPC. The best we can do for a cloud tutorial today. And the last thing I'll point out, which is so immensely cool, is that just think about this for a second. So you are on your VM, you're on your HPC 7G instance, and you have Flux as essentially the system scheduler, but it's emulating a job. Under Flux, we're deploying user space Kubernetes. When you run lamps in Kubernetes, you are deploying Flux via the Flux operator. So we have Flux in Kubernetes, in Flux, and then in there, that's where you're running lamps. This is the ultimate turducken, folks. And if you don't know what a turducken is, we have a link to teach you all about turduckens on Wikipedia in the tutorial. I realize that not everyone knows what that is. A quick primer on Kubernetes, if you've never used it before, kubectl, or sometimes pronounced kubectl, is how you interact with your Kubernetes cluster. Everything is YAML. YAML files are applied or created to create different abstractions in the space. If you've never done this before, look at the files before you apply them. Try to understand the structure. There's going to be metadata, a spec. A pod is the smallest unit of abstraction that you can create. It is basically a holder for some number of containers in a resource set. Like, okay, I want to run my application with engine X, and I want it to have this specific set of resources. A job was added with the batch working group. So the batch working group was created in 2022. And it was the first time, because of all this AI ML workloads that were starting, that there was an abstraction in Kubernetes that would start, be running, and then complete. Because traditionally, Kubernetes was used for like keeping your website running, and there wasn't this desire to have a completed state. All right, so we're going to jump back to the tutorial. And I want to point out that we do have a survey that we'd like your feedback on. We'll remind you again at the end of this talk. I also want to point out that we have an immense set of collaborators, academic and industry, and we think this is really important to really do good work in converged computing, and we are immensely grateful for all of these collaborations. So, on that note, I think we can open it up for questions.
First question, just reading out, is can we post the link to the survey in the chat? Yes. I don't have the link though.
I do have the link.
Chat.
I will grab it for you.
And just following up while Vanessa's grabbing that link on one thing I was going to say about the turducken or Fluxception deployment strategy. Yeah, it's probably not the most useful in production, but the fact that you can do it is indicative of the flexibility of the deployment, and what would be useful about that setup would be deploying Kubernetes or Usernetes in particular underneath Flux as a job, because that's something that converged workflows are really demanding right now. And the other thing that Vanessa may have mentioned, if so, this is a bit of repetition, and that is it allows you to reuse or use your existing HPC infrastructure and to dynamically deploy cloud-like environments on that existing HPC infrastructure, which is something that a lot of folks are asking for now.
Yeah, another note that I'll add that we actually didn't talk about, but Dan, you alluded to in your part of the talk. So we remodeled Mumi as a state machine design. And so that design is based on having a back kind of infrastructure that delivers events. So because both Kubernetes and Flux are able, you can basically watch for events, we can run Mumi as a sequence of steps, each an independent state machine on both bare metal with Flux and in Kubernetes. You run the same state machines in both environments. And we have a paper that we just submit that basically goes through kind of the workflow overheads of these environments. And it's really cool work.
So I will extemporize a bit on a few questions that came up, I think are related. I'm not sure, I think a couple of different folks asked them. And I know this is probably confusing. I don't know that we did a great job at this, is kind of delineating between a workflow and a workload, and what a workflow manager is versus what a workload manager is. And I think that's kind of key. Someone asked a really important question, like, are there overlapping capabilities between Maestro and Flux or other workflow managers in Flux? And my answer to that is no, and that's by design. We want to make sure that we deal with what we're best at, and that's workloads. I almost made that mistake. So what we kind of think of as the differentiating factor between workflow and workload manager is the workflow manages a directed acyclic graph. So it models a workflow as a DAG and then submits components like vertices of that workflow to a workload manager, which manages that component or that task as a job. And then dependencies can be expressed both in the DAG and in the workload manager. But I guess more broadly speaking, we think of the workflow manager as higher level, workload manager as lower level, more akin to or integrated with resource management and scheduling of specific resources. But of course, there's a tight interplay between those two. I think Vanessa mentioned this, but we have plugins for a lot of common workflow managers that will enable execution of tasks on Flux or by Flux from the workflow managers. So hopefully that's not too confusing. If you have any more questions about that, we're happy to talk about it. One other thing I'll mention, there was another really great question about, and this was related to the workflow versus workload kind of implicitly. I believe Jack was asking about managing, or how does Flux model resources, and implicitly, like, is that a DAG? Not really. It's so Vanessa talked about this a little bit. Currently, the resource graph is a directed graph, but it's a tree representation, and it represents kind of vertices as, think of them like nodes, cores, memory, etc. Generally, and then the relationships between them as kind of containment. So the edges would be like a node contains a core or contains a socket. And then in order to match a request for resources or a job request to that graph, we perform a traversal operation. So a depth first search traversal that uses all sorts of pruning strategies in order to optimize that search. So it's not actually representing a workflow as a DAG, it's representing the resources and then picking which ones are suitable for a particular request.
I'll add one point to the discussion on workflow versus workload. Flux does provide handles that make it easy for workflow managers to do things. So for example, you can specify depends on to be able to say like this step B depends on this step A. And so that's a very simple abstraction, but when you add that to a workflow manager that knows how to put things together, possibly is using the Python SDK, you can build your more complex DAG. And actually the Kubernetes has a similar, it has an abstraction called a job set. Job set also has a depends on that is inspired from Flux. We sort of contributed that name. If any folks have questions they want to ask, if you raise your hand, we can unmute you. You can also add it in the chat. I'll give folks a second, and then if there aren't questions, I'm going to show you how to set up the workspace because the notebooks look a little bit differently this year. Okay, I'm going to share my screen. Third time's the charm, right? Yeah, right. I'm unmuted. Share the meeting in progress. Alrighty, so this is dark mode. It's beautiful. And I want to show you how to set up the workspace so it's kind of pleasant to work in. So this year, we actually took many of our notebooks, and instead of like awkwardly executing Flux commands in the IPython notebook, which doesn't make a lot of sense, we refactored it to be Markdown. And so what you can do is you can click this icon here, Terminal. If you're not in the launcher, you can do File, New, Terminal. That's right there. And then what you can do for your workspace, so let's say that we go in tutorial and we're saying, okay, let's start with chapter 1. You open your notebook, you can actually take this terminal and drag it so it's right alongside here. So now what I can do is I can look at the markdown. I can also, copy paste things. And this is we think it's a more sort of natural or realistic environment for being on a cluster. And so what we wanted to kind of get a sense of next from the audience is we are able and willing to kind of walk through some of the content here, or actually walk through content that any folks are interested in. Maybe we can do a set of hands or hear from the audience about whether you want us to walk through things or leave you alone and we're here to answer questions. Does anyone have preferences?
Is anyone not able to get into the notebook or is having difficulty too? Another question.
Could be that folks are just working through the notebooks and all is good. Okay, we will be here. If you have any questions, want to talk, anything, we're here for you. Let us know if you run into any issues too.
Yep, we're happy to take time to go through any of the examples and any of the chapters that you think are interesting or complicated or not working properly. Oh, yeah, that's too bad. Hard to copy paste the password. Yeah, I'm not too surprised by that, unfortunately. We learned after 3 experiences of this not to put complicated and easily confusable characters in the password either. Although we did debate quite a bit over whether to have the exclamation mark or not.
Yeah, there was quite a bit of debate on the exclamation mark. And if you look at our passwords over time, it's like a slight migration as over time of what initially was the +1 exclamation mark creates excitement. I think so too, but when you put an exclamation mark in your terminal, it can create trouble too. We're also interested in feedback. If anyone has a request for a workflow manager that Flux isn't a backend executor for, we're interested to get that feedback.
And feature requests and collaboration.
Yeah, we love
collaboration
collaborations.
notes,
If you want to work with us, we really would like that.
I think actually, so that's another great question. It depends on how high latency, of course. If you're talking about like it takes minutes to send messages, that might not work so well. But the heartbeat system for Flux is tolerant to higher latency networks. Think Ethernet. You can easily deploy Flux across clusters. Well, not easily. You can deploy Flux across clusters. You can easily deploy it across nodes. And I think if I remember correctly, I'd have to dig into some of the settings. You can tune that timeout behavior too. You can tune the heartbeat.
You can tune the
intervals and
timeout
stuff
of the
like that.
heartbeat. I've done that.
Okay. Yep.
I made a little watcher and it printed a little emoji heart. It was pretty cool.
Yeah. There's actually if you take a look at some of the intro material, especially I don't actually know whether we have this, the Flux top. Maybe that's not in the intro material, but anyway, the Flux top command, I encourage you to try that out. It's really cool. It shows the heartbeat as well in the terminal.
Yeah, for advanced users, when you use the journal consumer and other Flux Python SDK endpoints to subscribe to events, you can subscribe to job events, you can subscribe to just heartbeats, you can select specific events. So for example, for Flux Sched, and it's a really powerful interface for building custom tools, custom orchestration. We've really just started to kind of dip into it. Yes, that's correct. So you can choose whatever username you like. Try to choose something unique, because if someone else has made that same choice, you're going to be sharing an instance and wonder why there's all these files in your notebook directory that you didn't create. But then the password is the one thing that you need to know. And we posted that up a little bit in this chat.
Okay. This is a really good question. This is yet another really good question. Difference between Flux Batch and Flux Submit. So Flux Batch is actually a unique thing that, well, they're both kind of unique, but Flux Batch does one additional thing that you can use to create nested instances. So Flux Batch will actually create another instance of Flux as a job underneath the top level instance. And that's one of the techniques you can use in order to tune Flux behavior across a hierarchy. So you can have a Flux batch script, you can submit a Flux batch script, within which you have yet another Flux batch script, which creates a Flux instance across a subset of those resources. And again, you can choose how you instantiate Flux. You can tune the queue behavior, the scheduling behavior, etc.
Yeah, so imagine that you have 4 nodes. Let's say that 2 of the nodes have really awesome GPUs and then 2 of them are CPUs. You would run a Flux batch on the CPUs and you could run a Flux batch on the GPUs. Maybe for the CPUs, you say, you know what, I'm going to be running a lot of really quick stuff, so I'm going to use an algorithm called Simple Sched that's going to have a really high throughput for running stuff. Under your GPUs, you're going to say, okay, I'm going to use just Fluxion, because you need to use Fluxion for GPU support. I want this particular binding. Within this Flux batch job, I'm going to be running a Flux submit for different components of the GPU work. And so both of those 2 instances are under your main parent instance of your job. So that's the hierarchy that you can, I hope you're seeing in your head right now.
Yeah, and it's another interesting and important point, because you can use the hierarchy to partition the resources, and that can actually accelerate graph traversals and scheduling. So if you had to submit jobs to the top level scheduler, that top level scheduler is representing and scheduling resources for the entire resource graph, which can be extremely large if you're thinking like El Capitan scale. However, if you want to partition your resources in such a way that you have, an ensemble-based workflow, you can have a sub-job submit resources to the instance itself. So the job-based, the allocated instance. So then you don't have to hit the top level scheduler over and over again. And that's something that you can use to dramatically increase throughput. Yeah, Flux Submit. Flux Submit executes the program that you provide as the first program within the enclosing Flux instance. Flux Batch creates Flux as its own initial program underneath that Flux instance. And therefore Flux Batch can have its own scheduler. So it instantiates like the tree-based overlay network, the scheduler, the queuing mechanism, the queue manager, sorry, etc. Oh, it looks like we got another question about unsetting the LD library path. I actually didn't notice that.
So I don't think that's actually required. I think that's just showing you an example of using env remove as a command line parameter. Because we didn't need label IO. We probably should have just done like pancakes or something, not LD library path, because that's kind of an important one. that would actually mean something, unlike the pancakes, you know.
Anyway, Eric, circling back to your question, I hope I answered your question earlier. Your understanding is correct.
Yeah, so by default, we have, I forget the name, we have sort of a curly F that, so this is configurable, but in the Flux job identifier. Now, there is a part in the Python, is it the Python tutorial? Yeah, in the Python tutorial that will show you all of the different ways you can represent a job ID. So you can remove that curly F, because I've been in environments where it does really weird things to the terminal. You can just have a regular F. You can represent it decimal, integer, different kind of hex formats. You can represent it as an emoji, and you can also represent it in words. So for example, imagine if you're calling the hotline, you're like, hello hotline, I'm having trouble with my job. You could read a long number, or you could read a sequence of words that's actually much easier to understand. So yes, the Flux job name does have a curly F. I don't know the story behind that. Probably Tom Scoglin would be the right one to ask about that, but it doesn't have to have a Unicode character.
Yeah, it has to do with the 58-bit encoding and also the high likelihood of generating unique job IDs across a Flux hierarchy. It's a Florin character. I unfortunately don't remember why that was chosen either. I was looking for the documentation on that. I remember reading it at some point. Tom or Jim or Mark would know the answer to that question a little bit better. But it is something that enables generation of unique job IDs across a hierarchy with extremely low likelihood of collision.
Yeah, Flux job last is also one of my favorite commands, because it's so nice. A lot of times you want to submit something and then interact with it, and you don't have to get the identifier. You just, either you just reference Flux job last or you pipe that into a variable. It's very useful. Yes, you can absolutely use Flux to run Python code. The Python tutorial is specifically showing you how to interact with Flux from within Python. So for example, if you're using SnakeMake, or if you're a developer for SnakeMake, which is implemented in Python, you want to add Flux as a backend executor, you would need to interact with Flux from within Python. And so that's what we're showing you how to do, so that in your Python scripts, you can have a Flux executor, you can bulk submit, you can do complex logic. You, of course, can do Flux run my Python script. That of course will work. My understanding of Balsam is that it's more of a workflow manager that is provided via an API. I don't think it is a workload manager, but that is my understanding based on looking at the code, getting it set up, trying to use it, and then realizing I needed to authenticate into resources that I didn't have access to.
Oh yeah, looks like everyone. Sorry, Sean, I'm going to unmute you. I didn't notice that you had your hand up. I thought everyone could unmute themselves. Go ahead. You're unmuted now.
Trying again. Okay, can you hear me?
Yep.
Okay, great. Hey, I've been using Flux for a tool that we use to submit jobs, and this might have been fixed in the last year or so. But I had an issue where I was given Flux mini jobs, 1,000 jobs or something like that, and there wasn't enough resources, so they would queue up and wait, which is fine. But the issue was I would also give them a timeout. I'd say run for 30 minutes, and a while back, I haven't. That 30 minutes started for when I submitted the job, and not when the job actually started to run.
Mhm.
So my jobs would start up and immediately, or quit because they used up all their time waiting. That is that sound right, or has that been worked on, or am I off base?
So there have been there's some corner cases where basically the idea is the enclosing Flux instance has a timeline as well because it is a job. So if you submit jobs that are going to take longer than that, we debated quite a bit about what the default behavior of that should be. Like, should it just not accept that job? Should it truncate the length of the job, et cetera? Am I understanding your question basically?
I think so, yeah.
Yeah, so we did do quite a bit of development on that. I struggle to remember what that issue was. I can look for that really quickly, and if you've got some different desired behavior for that, we're happy to talk about it. We might be able to pass on some parameter that would say, instead of just rejecting that job, truncate it. But best of my memory, what we did is we decided to reject the jobs because
Hmm.
that was the most expected. We thought that would be the expected behavior for most people, but we also recognize that other things would be useful too. So let me see if I can find that issue.
Okay. Yeah, I worked around it. Just heads up. The tool I have is called ATS. We use it for regression testing. But
Okay, I've heard of
I
it.
worked, uh, and I kind of worked around it by having ATS just kind of track how many, a little bit of tracking of how many jobs it could run at the same time, and then
Okay,
it would throttle. So it'd say, once
okay,
it hit the limit, it would stop giving jobs to Flux, and then that kind of worked around it. But it'd be great if we could just give all 1,000 jobs or whatever to Flux and have, without having to do that bookkeeping.
okay. Yeah, that makes sense. That's a good use case.
Okay, I'll mute myself. Thank you.
Sure. Yeah, sorry, I didn't realize no people couldn't unmute themselves. Yeah, if I'm gonna try to track the hands better, it's a little bit tricky, unfortunately, because the window that I track the attendees doesn't. It's a little bit cut off too. So, um, feel free to drop a message in chat, and then we can selectively unmute you. And it looks like there was another comment about GNU parallel inspiration for Flux bulk submit. Yeah, absolutely. Yeah, I think that was the original motivation for Flux bulk submit. The syntax is quite similar.
Yeah, I think this is in our resources, but we have a Flux cheat sheet that has some cool commands, and bulk submit is one of them. I will share that in the chat.
Okay, so going back to the question about the funny F, I finally found the documentation on this. Sorry it took me so long. What I said is largely correct, but if you want a lot more background on why it uses a 58 base 58 encoding, I will paste this in chat.
And one high-level detail, so that that repository, the read the docs for that particular documentation page that's under Flux RFC, that's how our developers maintain all of kind of the detailed documentation about how things work in those RFCs. So generally, when you're looking for the details of how something works beyond like a tutorial or a cheat sheet, this would be the place to come and search. It's on Read the Docs. And for folks that are going to be attending SC25 this year in November, we have a tutorial with AWS, and we are going to be demonstrating one of the workflows that Dan mentioned earlier, Moomy, running with the Flux operator in EKS, and it's going to be really fun. So we hope to see you there.
Sean, I dug around in the documentation, or I should say the pull request for FluxGet, and I found the discussion that I was referring to before. It doesn't look like it is in an issue. I'll paste this in, and if you want, you can create an issue on FluxGet where we can discuss exposing the ability to truncate the jobs to the user. It's definitely something we went back and forth on, as you'll be able to see in this discussion, the pull request.
That is a good question. So the notebooks themselves are on GitHub. Right now, they're in a branch that will be merged into main. What you won't, so in the past, when we deployed the tutorial in Kubernetes, that means that you can actually run the entire thing just as a container on your local machine. Because we're on an EC2 instance now that requires user space Kubernetes, you could technically run the first 3 still from a container, but Usernetes is not going to easily deploy from a single Docker container. So partially yes, to answer your question, and I can share a link to where I can probably merge it in now.
Oh, another great question. I just saw this. Can Flux be installed in any HPC machines, or is there something specific about running it at LLNL? Nope. The reason we're running it at LLNL is that we developed it, but it's actually run all around the world. I don't even know how many deployment sites we have at this point. You can run Flux underneath any workload manager, well, just about any workload manager you want. You can install it, provided that it has the required dependencies on just about any HPC machine you'd like, whether or not you want to use it as the system manager. So in other words, the resource manager and scheduler that takes care of the entire system is up to the system administrator, of course. But yeah, we have that. It's running on the Eldorado cluster at Sandia. I think I mentioned that. And there has been interest in deploying it in other places as well.
Yeah, we haven't done some kind of center registry to get a sense of all of the current centers. We made a map many years ago, I think 2021. We probably need to update that because it's out there in a lot of centers. We just haven't written them down. A really quick way to get started with Flux. So normally when I build it on like a VM or that sort of thing, I get code the components and I install them, and they're relatively simple to install. Libtoolize, automake, that sort of thing, and then FluxGet uses CMake. But there's actually packages on Conda Forge for most of the components. So if you're like sitting on a cluster with Slurm and you're in user space and you want to like quickly install it to your Conda environment and then start a Flux instance under your Slurm allocation, that would be a very quick up and running way to do it. We also have a kind of main Flux container with a really easy, you can literally shell into a single container and have Flux to play with. Let me prepare the command. So you do docker run it Flux. Don't worry, I'll share this in the chat. So if you want Flux in like 1 second on your computer and you're okay with Docker, just Docker run that and then do Flux resource list. You'll see your resources. If you do Flux start and then the test size equals 4, you will then get four nodes, not really 1 node that looks like 4. And then you can also run the Flux operator locally with kind. I usually do that when I'm developing something locally and I don't want to bring up like a Kubernetes cluster.
Just checking back on some of the questions before. Vanessa, did you answer the question about ALCF and Balsam and Flux?
I answered the best I could because I've only superficially used Balsam, that it's more of kind of a workflow tool with an API.
Yeah, I think that's true. I also don't have much experience with Balsam. I'm just reading some of the documentation, and to my mind, it looks like it's much more workflow oriented. It's a little bit difficult for me to tell how it interacts with workload managers or whether it also performs some of those functions. But it looks like it kind of is in a gray area between workflow and workload manager. I can't figure out much about its queuing algorithms except for that it is elastic, apparently, the queue in particular, or how it represents or whether it manages the resources. That I can't tell.
Yeah, Alfred, I didn't mean that we run Docker on premises. When I use Docker to kind of quickly test something in Flux, it's usually on my local machine. We also have Singularity and Podman on our clusters. I also prefer Singularity to the other rootless container options out there. I will leave it at that. Oh, that's great. Yeah, Singularity Hub feels like a long time ago now, but it was alive for 5 years, made 9 terabytes of containers that now live in an archive at Dartmouth. The reason that Singularity Hub went down is because we were able to finally push CIF files to just standard OCI registries, thanks to just the support for artifacts. So we didn't need it anymore, and that was the greatest joy of of many years, because it, you know, I maintained it all by myself. It's quite a bit of work.
Looks like the number of attendees has dropped a little bit at this point. Don't know whether folks have any questions or have run into any other difficulties. Guess I'll assume not. Nothing's popped up in chat. Got about 20 minutes left before we're going to close down this session. Is anyone interested in a walkthrough on Chapter 4? That's probably the material that would be least familiar to most of the attendees. Oh, looks like we got a couple yeses and 3 yeses. Great. All right. Why don't we, Vanessa and I can walk you through Chapter 4. This is the converged computing section, or much more converged computing section, where we talk about Flux with user space Kubernetes. Vanessa, you want to drive, or do you want me to drive? And we can add commentary as needed.
I'm happy to drive, and
okay.
Yes, I love your. Although sharing my screen has been challenging for me, we'll see if I.
All right. Well, if that doesn't work, I can share it, and you can add commentary.
Gotcha. Okay. Meeting in progress. Okay, here we go.
Yeah, so now that
Alrighty.
most of you have gotten through Chapter 1, sounds like we can jump right into the deep end. Just skip all that other material that's less interesting and go right to the advanced stuff.
Yeah, exactly. Okay, so here's Chapter 4.
One comment real quick, Vanessa, can you increase the size of your screen a little bit, or zoom in a little bit?
Yeah, let me do that. Let's move this guy
over. I can read it, but it's a little small. That's better. I can read that. Let me know in chat if that looks good.
Yeah, do folks want that bigger, or? Okay, well, tell me if there's questions or you want me to stop. So this is the script that is going to start user netties. I want to note that if you're actually running this on a production cluster, you would not have to do this. We added this so that you can experience it. And actually, I'm going to comment out a little command here that we had to basically rebuild the node, because we don't need to do that. So what's basically going to happen, I'll show you as this comes up. So by the way, we see that we have our fake 4 nodes, 256 cores. So you're in an environment and you want to start user netties. So we are going to run bash home Ubuntu start user netties. Okay, so what's happening is that it's saying, okay, I have Docker for my container. It's checking pre-flight. What that's doing is it's checking different kernel modules. I'm wondering, this seems a little slow, so we might actually want to have rebuilt the container. No, actually, that's pretty good. So when you bring up user netties, there's many different components that are created. There's different volumes that are created for what is essentially the kubelet, which is going to be a container that's running in the space. So that's what corresponds to var, opt, etc, as you'd imagine. The user netties node is what is running that main kubelet. There's also this network, and so the network is what's going to be using like Flannel, which is basically just Ethernet, but typically you use a bypass mechanism. This instance type, the HPC 7G, does have support for EFA, but because you only have one node, it didn't really make sense to add it to this particular tutorial. So the last thing that it's going to do after creation is that in order to interact with Kubernetes, you need to export this kubeconfig environment variable. Now that's in the case that it's in a location that isn't a default. So the default is actually in your home in a little directory .kube and then config. So what we do when we create this cluster is we basically copy that file there, and that's how you as the user, the kubectl command, you discover your different cluster resources. And so then we're basically going to be using kubectl to interact with our nodes in different ways. This coming up is a little bit slow. So just to give you some background, we pre-built this image on the node so you wouldn't have to build it. It doesn't take immensely long, but I think in practice, because we've been switching back and forth between instance types, There's a slight difference maybe in the graviton. Its graviton, I think it was 3e versus 3. And so that has shown to be a little bit slower for some components. So I'm not totally sure. I don't know, Dan, if you have comment about that.
Well, I'm testing it by rebuilding, and we'll see.
Okay, we'll race. Who's going to win?
Yep, who's going to win?
So by default, there's actually 2 roles that a node can take on. So when you first what's being brought up here is actually a control plane. The control plane is exactly what it sounds like. It's sort of a central management node for your cluster. So this is where the scheduler is going to live. A cluster can technically have more than one control plane. So if you have like a really big cluster, in practice, I have never had a cluster that has needed to have more than one control plane. If you're not running a control plane, then you're running a kubelet. And so what happens when you have multiple nodes is that the control plane comes up, all of your kubelets can come up at the same time. They are passed what's called a join command, which is basically the standard authentication handshake, like, hello, I know the secret for joining the cluster. And then they can all join that control plane at the same time. So even when you're starting user space Kubernetes on many nodes, in practice, it won't take more than maybe a couple of minutes to come up. This coming up is very slow, likely because of the environment that it's running on. The other kind of note about that is with respect to this environment, although we're running a control plane, we remove some labels and annotations from the control plane so that you can run work. Traditionally, when you bring up a control plane, it doesn't allow you to assign, for example, work that would normally go to a pod because it is labeled as the control plane. So that's that last step there where it says untainting control plane and labeling the node. That's what's going to allow us to run work. And if you go back here, so up here we see the discover. Can you see my cursor? Up here is the discovery token. This is what basically would be shared with another node if we wanted to give it access. All of these ports are also customizable in the case that you actually want to run 2 Usernetes nodes on one physical host. This is a contribution that I made to Usernetes. Okay, so we're ready. So if we do kubectl get nodes, not nods, nodes, there is our control plane. Great. I highly recommend that you run this command. This is going to give you auto completion so that you don't have to like copy paste a very specific identifier. So we can also get pods. So if we just do pods, so to step back, Kubernetes has the concept of namespaces. You will tend to create different applications in different namespaces. So for example, the kube system namespace is where you have a lot of services. The default namespace is the default namespace that you use. So when we just bring up a cluster and we get pods, this is showing us the default namespace. There are no resources there. But if you do all namespaces, we will see all of these services. And actually, let me make this a little bit bigger on this side so it's not scrunchy. There we go. You'll see all of what's running on the different nodes. So the Flannel, so that's networking, DNS is DNS, the API server, controller manager, and there's the kube scheduler. So you can look at logs for these things to understand. Okay, so we already looked at Flux start. Another kind of trick, you can do kubectl get nodes output wide. This is going to tell you the physical node that your control plane is running on. So the Usernetes happens to be prefixed with U7S on this IP, but you can also see the actual node name in terms of the IP and then this here. Okay, I'm probably going too much into details as I normally do. Let's get down into the tutorial. So these are some debugging tips that I'll show you if we run into an issue. So let's run some lamps, right? Okay, so let's start with lamps. And this is going to be a Flux run command, 1 node, 64 cores. We're going to ask for the CPU affinity to be per task. This -o means it's an argument for the broker, or sorry, an option. Current working directory, that should speak for itself. Here's the lamps command, size 444, and then the input file in that directory. Let's do it. So this is kind of emulating running lamps on, quote, bare metal. And I say bare metal because it's not really bare metal. And if you say bare metal, sometimes people have issue with that. So there goes lamps. Lamps usually starts up and then it's going to spit. Oh, there it is. 6 seconds. Great performance for a very small. And so one thing about lamps is you want to look at the CPU utilization to make sure that your network isn't throttling this. So when you tend to run, for example, Kubernetes with Flux on a cloud that doesn't have a bypass mechanism or a way to get good networking, you'll actually see these percentages in the 60s and 70s, not very good. And you'll see longer wall times too. Okay, so now we are going to install the Flux operator and run the same thing, but in Flux, Kubernetes Flux, the turducken. So the way that you install operators, again, like we said before, is by applying YAML files. We're on an ARM node, so we're going to install the Flux Flux operator ARM variant. So you apply. Each of those lines is something else that was created. So remember how I said there's many different kinds of Kubernetes abstractions. So you see things called like roles, role binding, a manager configuration. I won't go into details, but you can look at that YAML file if you're interested. So if we wanted to see the logs of the Flux operator, we do kubectl logs, namespace operator system, and then here's the Flux operator container. This is what a running operator looks like. It's not very interesting, but it's going to tell you that there's a health endpoint, the metric server, and it is ready to go. It is watching for you to create mini clusters and do something. So we're going to be creating this mini cluster for lamps. Let's take a look at that. Put this guy over here. No, not like that. Yeah, like that. Okay. So in these custom resource definitions, and actually any Kubernetes abstraction, you're generally going to have the section up here that says, this is what this thing is. This could be a job. It could be a pod. This is a mini cluster, an API version that coincides with that. Metadata. The spec is where the goodness is. So this is going to create a mini cluster size 1, 64 tasks, so using the full node. Logging quiet just means that we're not going to see output from Flux. If you needed to debug, you'd want to turn that on. Here are options for Flux itself. So for example, we're changing the view, the way that Flux is installed to match our system. So this needs to be ARM. And here's our main application container. This container does not have Flux in it. It has lamps and EFA, although we're not using EFA. We're going to say, okay, this is the working directory that I want. This is the command. And because by default, with these rootless containers, they bind a very small amount of memory to dev SHM, we have this special, this volume type where we add an empty directory so that we get the entire shared memory of the host. Probably too much information, but I figured I'd give that to you. So let's create our cluster. I probably should have done this before I started talking about it so that we could start pulling the container. So when you create something in Kubernetes, you do kubectl apply or kubectl create. I usually do apply. You can then do kubectl get pods. If you just do it once, it'll show you, okay, it's initializing. The initializing step is, so there's a couple of steps you're going to see. Initializing is when it's running something called init containers, and that is exactly what it sounds like. It means that basically that view that we specified, the other container that has Flux, is basically adding Flux to your container. So that's being pulled, that's going to be added. Another trick I like to do, so early in my days of Kubernetes, I used to be like, get pods, get pods, get pods, and then I discovered the watch command. Okay, so what the watch command is basically going to output something whenever there's a change of state. So pod initializing, that means that we've gotten to the point where we're actually pulling containers. And I do need to note that when you are doing experiments in the cloud, so once you pull a container to a node, it will be cached on the node. So if we pulled this container and we ran it and then we pulled it again, it would be very quick because the node has cached the container. However, the first time when you have to pull it, you really need to keep this in mind when you're doing a cost estimation for your nodes, because there are containers for AI/ML that are so chunky, they can take between 4 to 8 minutes, sometimes even longer, to pull once. And if, knowing the cost of GPUs, if you don't account that for your experiments, you're going to have a bad surprise. You're going to have a bad day. So please account for that. So this is still pulling. While that's pulling, let's look at some ways to look at pods. So if we do kubectl get pods, get pod, and let's do Flux sample. So by the way, this abstraction under the Flux operator is called an index job. So it is a job. However, indexed means that we're creating different replicas of the same container. In that case, one of the replicas is the lead broker. The rest of the replicas will be the workers. And so let's say that we wanted to look at this particular pod. So this index here, that 0, that means that it's the lead broker. If we had another worker, that would be 1, 2, 3, etc. So if we do output YAML, you'll see a YAML representation of your pod. And this is really useful when you need to, you know, look at something, debug something. It's going to have everything from the affinity. So this is going to do that mapping of 1-to-1. It has your containers and your command. The job completion index. So this is something that's automatically added to the job. So it's an environment variable that you can use to get the index of the container. Let's see. Lots of good stuff. So the config maps can be volumes. Another thing that's very handy to do is output JSON and then to pipe it into JQ. So JQR means raw, and then you can do like metadata, spell it correctly though, metadata. And then I could say like, okay, I want metadata, labels, and I want, you know, the namespace or something like that. So that's a very nice programmatic way to get metadata. Let's check on our polling. Oh, it's done. We missed it. Okay, great. So when you want to see your log, so this is what I was talking about in terms of a job having, you know, a state. It starts, it was running, and we missed it, and now it's complete. But it's okay. The reason that the job stays there in that completed state, and there's actually a time limit where it'll eventually disappear. It's not actually taking up any resource in the cluster now. It's just there so you can look at it. So we can do kubectl logs, flux sample 0. There's lamps, and guess what? It also ran in 6 seconds, if you remember before our lamps. And the CPU utilization is basically the same. So that was lamps. And here's an example of how to get the lead broker. I showed you this, items at 0 metadata.name. Then you could, oh yeah, so another thing that I can't show you well because the job is done, but when you add F, that would basically keep the log hanging. So a lot of times when we're running experiments, we'll do F, and then we'll have it streaming into a log. So we can see it while it's particularly running if you use T. Okay, so I noted that the job is still there. So if I do kubectl get pods, I can still see it's completed, but maybe I want it to, you know, clean up. So I'll delete it. Now it's gone. Okay, great. Let's see how we're doing for time. Oh, we have 5 minutes. So what do folks want to see? Do we want to see, let's see, I can show you Kubeflow Trainer, Moomy. I think we should do this one. So I want to quickly show you an example of running lamps orchestrated with Flux in a really cool way. So what we're going to do now is install something called Ingress. So this is going to allow us to interact with ports in our cluster from our hosts, because by default you can create networking spaces within sort of components of your cluster, but to get it back to the host, you usually need something that is akin to Ingress and to expose ports. So we're going to be creating an ML server deployment, this guy, and I probably don't have time to go over those details. So I'll basically say that it's going to be a deployment and then different endpoints and services for us to interact with. So let's create that. Hopefully the poll isn't too long for the containers. Okay, we just created the ingress. We can look at the different components like this, and you can explore these later. Another useful command is describe. So I can say do describe pod ML server. This is going to give you more kind of events of what's going on. So here's my secret key is noodles. Everyone knows my secrets now. So yeah, so right now it says that it is polling. Hopefully, so I'll show you watch now. Get pod watch. Oh, it's running. Okay, that's great. So this is a server. So it's not going to complete, which is probably good for us. So let's first do some training, shall we? So I have a script. Oh yeah, so we can actually test this command. So this would be me interacting with the API, with curl. There it is. This is a server I built called Django River ML. It is a streaming machine learning server, meaning it is hosting models. You send data to it to train, and you send data to it to predict. So what we have here is a script that is going to create models in that server, and they are going to have very entertaining names. Let's see, what are they going to be called? At least hypothetically. Don't know what it's doing. I have the script here. Okay, I'm not actually sure what it's doing. Oh, there we go. seems, so we have Boopy Banana, Chocolate Carrot, etc. That also shouldn't take very long. I'm not sure what's going on. So let me just quickly show you training, and then we'll probably have to end soon. So what this is going to do is this is going to basically run lamps, randomly selecting parameters from a range. So it's saying, okay, running iteration 0, which shows an XYZ. It is taking those parameters and then the lamp's runtime, sending them to the server, to each of the 3 models, and then saying, okay, use this data to train. And so it's going to do this for 20 iterations. And then we have another script that basically just switches the endpoint and says, okay, I'm going to run lamps again. I'm going to give you the X, Y, and Z, and I'm not going to give you the runtime. You give me a prediction for the runtime. And then at the end, it will show you the different parameters. And so we won't have time to get through this, because actually a better model, you want to do more than 20 iterations. But this is what I ran earlier. This was actually on a much smaller instance, the T4G2 extra large. And let's see, I believe, yeah, gassy nunchucks did very well with an R-squared error of 0.88. So we are at time. I'll point out that there are examples of running some Mumi components, and then an AI ML training job. Take a look at Kubeflow Trainer. It's a great project. It is what the community is using in the larger sense for training in AI ML. From a design strategy standpoint, I think we will do much better off using the tools and the methods to deploy these ML training and inference that the larger community is using, as opposed to developing our, what's our in-house kind of niche tools that there's only like 3 developers for. Alrighty, we are out of time. I guess if there's any questions, we'll take it. I can stay a few minutes over, but thank you everyone for coming. If you have further questions, please contact us. We have a Slack. You can post us a question on GitHub. You can email us. You can send me a carrier pigeon, but let me know he's coming so I open the door and I don't like push him away. If you haven't yet, please fill out the survey and let us know how we can do better next year. I kind of like walking through the tutorial content. I get a sense we should do that more next year after we answer some brief questions. So thanks again, everyone.